The next set of identities that we're going to begin to explore are called the double angle identities, or the double angle formulas. Now we can derive these based on what we've already been able to verify in the past. So let me show you what I mean. Sine of 2 theta. Well, first of all, we need to realize it does not equal, and where should I put that at? It does not equal 2 times the sine of theta. Those are two completely different types of equations. I can't pull the 2 out of the argument and stick it in front, although some people like to do that. All right, just want to throw that out there. All right, so sine of 2 theta. Well, what if I wrote sine of 2 theta? Oh, sorry, sine. There we go. Sine of 2 theta as the sine of theta plus theta. You remember that identity? Well, that identity that we had when we had was the sum formula for sines said that this would equal the sine of alpha, which is the first one, times the cosine of the second one, plus the cosine of the first one, and the sine of the second one. I may have read those a little bit backwards based on what we've done in the past. Then we look at that, and I have sine of theta, cosine of theta, plus basically the same thing. And so what I have now is I have 2 sine theta, cosine theta. So we just have proved the identity, the sine of 2 theta, or the double angle of theta, equals 2 sine theta, cosine theta, which is the identity that we had right there. Likewise, cosine of 2 theta, I think I could write that one. Cosine of 2 theta is also, if I were to prove it or verify it, I could write it down as a sum formula of 2 angles. And if we remember that one correctly, that was the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. And then that shortens down to cosine theta times cosine theta is cosine squared theta minus sine squared theta. So it's just a process of using some previous identities to develop more identities. And then the tangent of theta, if we remember that, that model, tangent of 2 theta can also be written as the tangent of theta plus theta. And I believe that one said the tangent on the numerator was the tangent of alpha times the tangent of beta all over 1 minus tangent of alpha. And actually, that was a plus right there, wasn't it? And the tangent of beta. And if I combine those two, I have 2 tangents of theta on the top. And on the bottom, I have 1 minus tangent squared. And so identities, all 3 of them, the double angle identities, all verified. Now let's look at some situations and try to find some exact values of some angles that we can find best by using these double angle identities. All right, let's see what we can do with this situation that we have here. We're given some initial information that the sine of theta equals 5/13, or 5 over 13, and the angle is expressed over in a quadrant 2. So we developed a picture that represents that. My sine, so my y would equal my 5, my radius equals my 13. And I want to find, from this one, let's practice finding the sine of 2 theta, cosine of 2 theta, and the tangent of 2 theta. All right, in order to use and find the sine of 2 theta, I need to have sine theta, which I do, but I need to find a cosine theta. So what's the cosine of theta? Well, cosine theta involves finding this value of x, like we've done before. And this x, we can go ahead and do the Pythagorean theorem, or by now, I'll allow you to accept the fact that it's a 12. We know that 5, 12, 13s are some typical right angles. And so my value of x is a 12. However, since it's in the second quadrant and I'm looking for the cosine, are cosines positive or negative in the second quadrant? They're negative. So this x then would equal a negative 12. All right, so now I think I have all the information I kind of need to find out what is the sine of 2 theta. That's going to equal 2 times the sine of theta. The sine of theta we already have is 5/13. Times the cosine of theta. Cosine of theta is adjacent over hypotenuse, which is a negative 12/13. And from there, it's a matter of just plugging away and going from there. So 13 times 13 is 169. 2 times 5 times 12 is 10 times negative 12. That's 100 negative 120 is my value. And from there, it does look like I can probably go ahead and reduce down if I want to reduce down from there. If not, we'll leave it right there for now. Well, maybe I can't reduce down. All right, so the sine of 2 theta, negative 120 over 169. Now the cosine of 2 theta, how do we find that? Using the double angle identity, it's cosine squared. Cosine we've discovered was negative 12 over 13 squared minus sine squared. Sine was 5/13. Square that. And so that gives me 144 over 169 minus 25 over 69. 169. And that equals, what is 144 take 125? 119? $119 over 169. And the next one we want to find is our tangent of theta. Or sorry, the double angle of tangent. Again, we have all the characteristics we need to have. So 2 tangent of theta, so 2 times the tangent of theta. Tangent was opposite over adjacent, which is in this case 5/12. And that's a negative, isn't it? Yep. That was in the numerator, and 2 times tangent, and then in the denominator, 1 minus tangent squared. Tangent again, it was negative 5/12. And I'm going to square that die. All right, and let's just kind of work it through and see if we don't make a mistake. The numerator becomes negative 10/12. The denominator, I got some work on it to go. 1 minus, so minus 5/12 squared becomes, so that's 1 minus 25 over 144. Got more work here to do than I wanted to do. All right, I don't think I dropped any signs along the way. And then we invert and multiply on that one. So let me just come down right here and then. So this becomes negative 10/12 times invert multiply, which is 144 1/19. I guess I gotta go ahead and simplify it there. I'll do it later. 12 goes into 12 one time, 12 goes into 144 12 times. And that equals negative 120 over 119. Yep, there's the exact value for tangent of 2 theta. All right, you guys all right with that? First time we've seen double angle formulas, so we're given some new identities, but the process is fairly similar. Let's go ahead and find out the other characteristic we don't know. In this case, we didn't know the x. We had to find the value of x based on our initial conditions. That allowed us to help discover what the cosine was. And then from there, it's just plugging in the values, the exact values within the identities, and then being very careful solving them one step along the way. Well, look at that. It's asking us to find the exact value of 2 tangent of 15 degrees all over 1 minus tangent squared of 15 degrees. Now, isn't that convenient? It happens to line up exactly like the right side of my double angle identity for tangent. So again, this is just an exercise to let us know and be able to observe and be able to learn how to identify, get used to these double angle identities. And so if you saw this, I would hope you realize, okay, double angle identity in there. And that's the point of this exercise. So let's look at that and just work our way backwards. Do you know what our theta is? Our theta is 15 degrees. So let's rewrite this then as the tangent of 2 times theta, which is 15 degrees in this case. Tangent. So I'm asking what the tangent of 2 times 15 is, which is 30. And tangent of 30 is one of those exact measurements, those exact angles that we are able to see over and over again. It's one that I'm hoping you get closer and closer to committing to memory. Tangent of 30 is a root 3 over a 3. And there's the exact value of our initial statement. Now, sometimes it's useful looking at the double angle identities all instead of one terms. And so we're based off that, we're able to develop 2 more double angle identities for cosine. And this is based on the sine squared, cosine squared equals 1, the Pythagorean theorem. We're able to develop from that the cosine of 2 theta can either equal 2 cosine squared theta minus 1 or cosine 2 theta equals 1 minus sine squared theta. Again, there's so many different identities that we're going to be able to build off of our base ones. However, I just want to kind of highlight the ones that will probably be the most typical to use. So with these 2 new additions might be helpful for us to identify or to verify this identity up here. So I'm going to begin with the left side. It's not the more complicated side here, but it's the one that is using a little bit of the double identities. So let's rewrite this one as the cosine of 2 theta plus theta. You guys agree that's the same thing as cosine of 3 theta? And what was the addition formula for a double angle, or not a double angle, but a sum angle of cosine? That was cosine of the first term of alpha, or the first angle, 2 theta, times the cosine of the second angle, in this case is theta, minus sine of the first angle, times the sine of the second angle. All right, so that's based on an identity that we've explored before. From here, I see a cosine of 2 theta, and I'm going to write that in terms of cosines. So this part right here becomes then 2 cosine squared theta minus 1, all times cosine theta, minus the sine of 2 theta. I can rewrite that as the 2 times the sine of theta times the cosine of theta times the sine of theta. All right, what can we do now, folks? On the right, on this part here, I can probably distribute this cosine through all the way. And so I'm going to have cos 2 times the cosine of cubed theta minus the cosine of theta. I distributed the cosine theta to the 2 terms. Minus sine theta times a sine theta is a sine squared theta. All right. Sine squared theta. That's one, because it looks like I'm trying to get them all to be cosines to kind of help me out. Because I notice in my result of my identity, they're all in cosines. So I'm trying to gently remove all the cosines out. Sine squared is the next one to remove out. So 2 cosine cubed theta minus cosine theta minus 2. Sine squared theta was a 1 minus a cosine squared theta. Previous identity that we've explored. Let's distribute that all the way through. How many steps do I want to take here? Cosine theta, that becomes cosine theta minus cosine cubed. Let's distribute this negative 2 all the way through then. So 2 cosine cubed theta. I wrote that down 4 steps in a row, and this one as well. Well, that's how we do the work, is always make one change at a time if we can. So negative 2 times cosine, that becomes a negative 2 cosine theta. Negative 2 times that becomes a positive 2 cosine cube theta. Collect some like terms. It looks like I can collect my cubes. So I have 2 cosine cubes plus 2 cosine cubes, which produces 4 cosine cubes, minus a 1 cosine theta minus 2 cosine thetas is a minus a 3 cosine thetas. And that's what my right side says at the beginning of the identity. So we can say identity verified.